So I see all kinds of calculation and things going on, right? Kind of a nasty function to optimize. When we put on our grade 9 goggles, we see that it's a parabola, right? We get a t squared, and that's about it, right? There's a t squared and whatnot. So we do some sort of single variable optimization with this parabola, and we notice the following. If we plug in t equals 0, we get negative 12. Okay, so our lowest value is negative 12. And the hard thing to check is that it has a max. But it's a parabola pointing downwards. Right, so we're going to get some kind of maximum. And it turns out the maximum is about negative 3. Okay, so now let's think of what we've got. At this point, our function is outputting negative 12. Is that true? No. Sorry. Sorry, our value of negative 12 is coming from C2. Okay, we've got a value that's outputting 0. And all of our other values are negative. Right? This guy is negative, 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 and 0. Okay, so we get that the origin is our max. And this guy is our min. Okay, so those are our boundary points that optimize this function. One question that came up a couple times, so we did an example over a triangle like this. A couple questions from office hours were, why do we have these repeated values here? So we've got these repeated values because these two lines meet at one point. Right? So the min on this line is negative 12. And the min on this line is negative 12. So we get that value repeated. And we also get this value repeated because it comes up on C1 and C2. Okay. So it's the same point written sort of as part of two different calculations. Okay, yep.
If we're following that logic, wouldn't the max of the C3 and the min of C1 should be the same because they're all connected, no? If we're using that logic then.
Right, so the
max of C3,
max of C3,
and the min of C1 should C, because they're connected, right? Is what you're saying?
Right, so I'm saying that we get lucky and the max happens at the end point. Right, so this C1 min, the C1 min is out here.
Yes.
And the C3 min is over here.
No, the C3 max.
C3 max. Yeah, so the C3 max is somewhere in the middle.
Oh, okay.
Right, it happens not at a vertex.
Okay.
Yeah. Cool. I think this helps. Did that help overall? Yeah. Cool. Okay. Yes. Right. When we plug in this point 0, 4. So this guy here at 0, 4 is giving us our min value. Okay. We've got a couple minutes left before break. So what I want to do is I want to briefly talk about how substitution works in one variable, and then we'll start after the break going into how substitution works in 2 variables. Just before I erase this, final questions, comments? Yes?
You didn't take the derivative of C sub 3, did you?
Right, I did it very sneakily.
Oh.
Yes, so none of the calculations for these mins and maxes is on the board.
Okay, right.
Yeah. I'm trusting that you can take the derivative of this during the break or at home. Very brief refresher on single variable substitution. So when we're doing integration, we can often change variables. So we say, aha, we've got a function and its derivative happening in the same integral. This is beautiful. Right? This reminds us of the chain rule. Function and its derivative. So we make an appropriate change. What do we get here? Right, all the derivative stuff goes and becomes du. All the g stuff becomes u. So what this does is it switches our variables to something that's hopefully easier to integrate. The simplest example of a substitution is something of the following form. We say, aha, we have a function, we have its derivative, now we've sort of got a nicer, simpler thing to integrate. So this process of switching the bounds usually trips people up. This is usually considered quite confusing. The idea is that when we're inputting x equals 1, we're inputting into this square function. right? So we should be inputting 1 squared into e to the u. We're inputting 2 into the square function. Right, we get 4, so we should be inputting 2 squared into our upper bound here. Okay, so this is the situation in 1 dimension. I want to talk a little bit about what this du does, just to shed a little bit of light on it. So when we start off with our integral in these terms, right, when we start off with it just in terms of x, then our Riemann sum is kind of equally distributed, right? We've got these really, really, really thin rectangles dx. All right, so these are initially the size of rectangles that we're using. But when we change variables, now those rectangles don't count for the same amount anymore. They're not going to be equally sized. So when we switch to new variables, they'll start off the same, sure. But each unit of area will get bigger and bigger when we make this switch. And that ratio of how big they become is the derivative. So this is du dx. Okay, things are sort of stretched out when we make this change. So what we'll investigate after the break is how this story plays out in multiple variables. Right? What changes do we need to make to this story to get integration by substitution to work in 2 variables? So feel free to go grab a coffee, stretch your legs, and we'll pick up at, let's say, 2:10. Okay? Pick up at 2:10 with the notion of substitution. And if you have questions, please come on up.